if you want to look at this question related to a piecewise defined PDF, where we're told that fx of the PDF is equal to x for x between 0 and 1, it's equal to 2 minus x for x between 1 and 2, and 0 otherwise. So the first part asks us to graph the PDF, so let's do that. So here we'll take our vertical axis, this is our horizontal axis. Right, so over here we have the PDF fx, and here we have small x, the values the random variable x takes. Now we know for x between 0 and 1, so this is 0 and this is 1. So we can see over here the PDF is just equal to x, right? So this is fx is just equal to x, and this point we know is 1 1, right? This is 1 because over here when x is 1, the PDF value is also 1. Alright, so this is 1 1, and then for x between 1 and 2, if I take this to be 2, the PDF is 2 minus x, so it would be also be plotted something like this. So this is 2 minus x, it's a downward sloping line, so minus 1. So this is fx is 2 minus x in this region. In this region it's x, it's like a piecewise defined PDF, right? Where between 0 and 1 it's defined as x, between 1 and 2 it's defined as 2 minus x, and obviously this point is 1 1 because over here when you put x1, the PDF value is 1. Over here also we can see that when x is 1, the PDF value is 1. And this point is essentially to 0, because when you put x is equal to 0, you get uh yeah, so you get the PDF value. So when you put x equal to 0, you get the PDF value 2. Right? Sorry, my bad. When you put x is equal to 2, you get the PDF value 0, right? So this is how we can plot a PDF, and it's 0 otherwise. Let me just show that part also. Okay, it's 0 otherwise, right? So otherwise, it's 0, right? So basically, it's some, like if you want to show this, so it's 0 over here, and it's 0 over here, right? So between 0 and 1, we plotted the PDF as the y is equal to x line, right? So fx is equal to x over here. And then we know, okay, at this point, right, the point where the PDF changes form, it's like the point x is equal to 1. And at this point, we can see the y value is 1, like, and it's 1 whether you plug it in x or 2 minus x. So it's like a continuous PDF over here, right? So let's look at the next part, which is that they're asking us to show that the density has the properties of a proper PDF. Let's do the next part. So we know the two properties of a PDF. We'll first show the PDF is non-negative, right? So the two properties, one is that it's non-negative, the other is it integrates to 1. So we'll first show the PDF is non-negative. What do we mean by non-negative? So the PDF is non-negative, i.e. what we mean by this is that fx is greater than equal to 0 for all x, right? This means for all. For this, let's look at what the PDF is. Now, fx is given to us as x, right? For x between 0 and 1, let's just write it down, 2 minus x for x between 1 and 2, and it's 0 for all other values of x. For all other values of x. So let's show that this is this is greater than equal to 0 for all x, right? So here you can see, because x is between 0 and 1, so when the PDF value is just x, so it's greater than 0, right? Because obviously the value of the PDF is just the value of x, and the value of x is greater than 0 in this particular region. When x is between 1 and 2, 2 minus x is always greater than 0, right? Because from 2 you're subtracting a number which is less than 2, right? So you're going to get a positive number here, and here too it's basically 0, so it's 0 here anyways. So from here we can see we've looked at all possible intervals, and so fx is greater than equal to 0 for all x, right? Because it's greater than 0 when you're looking at 0 to 2, and otherwise it's equal to 0, right? So we've shown the first property that the PDF is non-negative, it's always greater than equal to 0 for all possible values of x. We'll show the second now. The second is So we want to show the second property. The second is that we will now show the PDF integrates to 1. Just like the PMF sums up to 1, we know the PDF has to integrate to 1. We'll now show the PDF integrates to 1, i.e. So this basically means we want to show that to integrate our PDF from minus infinity to infinity, we get 1, right? So now if we look at minus infinity to infinity, if you want to integrate fx dx, so this just simply reduces to integrating it from 0 to 2 fx dx. Why is that? In general, you integrate a PDF from minus infinity to infinity, but in this case, the universe is restricted from 0 to 2, where the PDF is non-negative, right? So PDF is only non-zero, sorry, non-negative, I'm saying a non-zero. PDF is only non-zero from 0 to 2, right? So in general, yes, we need to show the PDF integrates from minus infinity to 1, but in this particular case, the universe is restricted from 0 to 2, where the PDF is non-zero, right? So we can just write the integral where from 0 to 2, where our PDF is non-zero. Now we have to break this PDF at x is equal to 1, right? We have to break it at this point. We have to not break the PDF, we have to break this integral at this point at x is equal to 1, right? So basically, we will have to write this as 0, 1 x dx, because we know from 0 to 1, the PDF takes the form of x. And from 1 to 2, the PDF takes the form of 2 minus x, right? So we have to break the integral at the point where the PDF changes formula, right? So basically, the idea is that we have to um, right, so we have to split. So this is why, this is the point of using a piecewise. This is what becomes relevant when you're looking at a piecewise defined PDF, right? You have to split the integral where the PDF changes from, right? So we have to split the interval at x is equal to 1, where the PDF, where the formula for the PDF changes, right? Where the formula for the form for PDF changes, right? So since it's a piecewise defined PDF, so we need to split this integral at the point where the PDF changes form, and that's x is equal to 1. Because before x is 1, between 0 and 1, it takes the form of x, and after that, it takes a value of that. Let's just make this more explicit, right? We can see, right? So basically, my bad, right? So here it's x, right? And here it's 2 minus x, right? Between 1 and 2, right? So we have to change the form, split it at x is equal to 1, because we're looking at a piecewise defined PDF, right? So now it's just integration. Now we just need to integrate this. So we know the integral of x is x squared by 2, 0, 1. Plus the integral will do 2 minus x is from 2x minus x squared by 2, 1, 2, right? Let me just clear this up. And then when we do this integral, we were doing x squared by 2, 0, 1 minus 2x minus x squared by 2. This was 1 to 2. So then this just becomes 1 by 2 minus 0 when you plug in the limits. 2 minus 3 by 2, and you simplify this, it's equal to 1. So we've shown that the PDF satisfies both of the properties that you need for a valid PDF. Number one, that it is non-negative, it's greater than equal to 0 for all x. Second, we have shown that the PDF integrates to 1. Right. The next part is asking us to find the probability that x takes a value between 0.5 and 1. So just let's recall something first. So recall that for a continuous random variable, right? We're looking at a continuous random variable. Area under PDF gives probability. This is the most important thing that we need to keep in mind, that area under PDF gives probability. We know we can find area under curve using integration. It gives probability, right? Area under gives probability. Okay, sorry. Probability. So to find the probability that the continuous random variable, let's just write as CRV, continuous random variable lies in an interval. Right, so we want to find the probability lies in any interval. We just integrate the PDF over that interval. right? We know for a continuous random variable, area under the PDF gives us probability, and area under the curve can be found through integration. So if we want to find the probability that the continuous random variable lies in any interval, we integrate the PDF over that interval, because that will give us the area for that particular area of the particular region, which is going to be equal to the probability of the continuous random variable lying in that region, right? So if you want to find, like, let's just clear this up. So we want to find the probability that x is between let's just clear this up just a second. So we want to find the probability x is between 0.5 and 1.5, right? So we just integrate our PDF from 0.5 to 1.5 fx dx, right? Because when you integrate our PDF between 0.5 and 1.5, this will give us the area under the PDF, right? From x is 0.5 to x is 1.5, which would be equal to the probability that x lies between these values, because area under the PDF gives us probabilities in this case. Now again, because this is a piecewise defined PDF which changes form at x is equal to 1, we need to split our integral at x is equal to 1. Right? If this was, for example, just 0.5 to say 0.8, then we wouldn't have to change form because we would be in the upper part of the PDF throughout. If this was, say, between 1.5 and 2, we again wouldn't have to split the integral, because we'd be in the second part of the PDF throughout. But here, because we have the part where it splits, like, one part of it is before the split, one part of it is after the split, so we have to split the integral where the PDF changes form, right, at 1. If this was like 0.5 to 0.8, then this would just have been x dx, right? If this was just like 1.5 to 2, then this would just have been 2 minus x, right? But over here, because we do have the 1 a part of it which changes form, so we would have to split it up. So this is about a piecewise defined PDF, right? So basically, so we have to split it at 1, where it changes from x dx, plus 1, 1.5, 2 minus x dx, right? So again, it's important to keep in mind, okay, we have to split the integral. So split the interval. We have to split the interval at x is equal to 1, where the formula or the form of the PDF changes, where the formula for PDF changes, and this is a piecewise defined PDF. Right, so now we just have to do some integration. So this is just again x squared by 2, 0.5 to 1, plus 2x minus x squared by 2, 1 to 1.5. And then when you plug in the limits, you get 1 by 2 minus 1 by 8, plus 15 by 8 minus 3 by 2, and this turns out to be 3 by 4. But let's just graphically show this area on the PDF. So if we do that, we know our PDF is something like this. Sorry, no, no, sorry. Okay, something like this is fine. Right, this is fx, this is x, this is 0, and this was, this was 1, and this is also 1, and this was 2. Right, so we basically want to find the area between 0.5 and 1.5, right? So this is 0.5 and this is 1.5. So what we're saying is that this area is the probability that x is between 0.5 and 1.5, which we found by integrating the PDF between 0.5 and 1.5, which gives us 3 by 4, right? Because we know area under the PDF gives us probability. So if I'm finding the area between x is 0.5 and 1.5, that's the probability that x lies between 0.5 and 1.5. And we know we can find the area under the curve by integrating. So here the curve is the PDF, so we just integrate it from 0.5 to 1.5 to find this area. Right, so it's this entire area.